Here in this slide, we want to see routing concepts. But first, let's see characteristics referred to when discussing networks. Network characteristics include topology, speed, cost, security, availability, scalability, and reliability. With topology, bear in mind that we have two different kinds, physical topology and we have logical topology. Physical topology, it's in fact the arrangement of the cables, network devices, and end systems. Physical topology describes how the network devices are actually interconnected with wires and cables. On the contrary, logical topology is about how devices appear connected to network users. So, this is the difference between physical topology versus logical topology. With physical topology, how devices are actually interconnected is intended, whereas in logical topology, how network devices appear connected to users is intended. So, with logical topology, it describes the path over which the data is transferred in a network, and as I said, how the network devices appear connected to network users. So, everything in logical topology is from the perspective of the users, whereas in physical topology, we see the actual interconnection of wires and cables and devices. Next network characteristic is speed, is the measurement of the data rate in bits per second, so it is shown as bps, bit per second, b/s, of a given link in the network. Next, we have network costs. Cost is not only the cost for purchasing, but also installation costs as well as maintenance costs. They're all included in network costs. General expense for purchasing of network components as well as installation of them, as well as maintenance of the network, they are all intended. Then we have security, indicates how protected the network is, including the information that is transmitted over the network. So we are not only talking or caring about network security, device security, or technical security, but also information security. It is important to make sure that the information transmitted over the network is protected as well as the network itself. Availability is the next network characteristic, and it refers to the likelihood that the network is available for use when it is required. We then have scalability to indicate how easily the network can accommodate more users and data transmission requirements as they increase, because we know that over the time they increase, and how we want to accommodate more users and data requirements is what scalability is about. Finally, here we have reliability, very important concept in networking. It indicates the dependability of the components that make up the network itself, including the routers, switches, PCs, servers, and very important to know that reliability is often measured as mean time between failures. So remember, reliability is measured by MTBF, stands for mean time between failures, in order to demonstrate the dependability of the components that make up the network. Next step is about routing. Why routing? We need routers in order to interconnect networks. Router connects one network to another network, and therefore they're responsible for routing traffic between different networks. Routers and routing, they determine the best route to get to destination. For this, they need what we know as routing table in order to determine the most efficient path to reach the destination before forwarding traffic out the exit interface to the next router along the path to the final destination. So two primary functions for routing. Routers are here in order to determine the best path to send packets for the first thing, and routers are here in order to forward packets towards their destination for the second. So routers interconnect networks, and router is responsible for forwarding packets from network to another, from the source to the very final destination. Multiple networks and a router require multiple interfaces that each belong to a different IP network. So if you have a router with two active interfaces at the moment, each of those two interfaces belong to a different IP network. And this is very important. Routers break the broadcast domains. So each of those two active router interfaces belongs to a single and a different broadcast domain. Router interfaces, they're used to connect LANs and WANs, local area networks and wide area networks. Local area networks, LANs, Ethernet networks that contain PCs, printers, servers in your local area, and wide area networks, they're used to connect networks over large geographical areas. For instance, they're used to connect to an ISP, for instance. So routers, they support multiple interfaces to connect LANs and WANs. Each interface belongs to a different IP network. What happens when a packet arrives on a router's interface? That router might be the final destination for that packet, or it may be just another hop on the way to the final destination, so it may have to send it to another router to reach its final destination. Routers, as I said, they use what we know as routing table, and routing table acts like a map in order to discover the best path to a given network. When a router receives a packet, it examines the destination address of the packet and uses this routing table or map to look for the best path to that network. As you can see, we need to open up the packet, see the header, read the destination to determine where it needs to go and what the best path to final destination is. We then need to encapsulate that packet into a new layer 2 frame of outgoing exit interface of the router, and then we need to forward it out towards the final destination. So for each packet, depending on the exit interface and the data link layer that the exit interface supports, router needs to encapsulate again that packet into new layer 2 frame of outgoing interface and forward it out. So when a match in the routing table is found, the router encapsulates the packet into the data link frame of the outgoing exit interface and then forwards the packet out that interface to its destination. I'll tell you more about this process in the next slide, but for now, I want to discuss packet forwarding mechanisms that happens in Cisco routers. Routers, they support three packet forwarding mechanisms. They support process switching, they support fast switching, and they support CF, stands for Cisco Express Forwarding. So packet forwarding mechanisms, we start with process switching. Process switching is slower and older packet forwarding mechanism. What happens is the packet arrives on an interface. It is forwarded to the control plane where the CPU matches the destination address of the packet with an entry in its routing table in order to determine the exit interface. The reason that this forwarding mechanism is slow is that it does this for every packet in a stream. It sends it to the control plane. CPU needs to match the destination address for every packet with an entry in the routing table for every packet, and then determine the exit interface. So it's slow. For fast switching, the second mechanism, that is a common packet forwarding mechanism that you will find in routers. It uses a fast switching cache memory in order to store the next hop information. And as you would expect when we use cache, that means that we're going to have some more improvements in the speed. Similar to process switching, packet arrives on an interface. It is then forwarded to the control plane, where the CPU now searches for a match in the fast switching cache memory. If no match is found, it is process switched. If a match is found, then it gets forwarded accordingly. But if no match, then process switched and forwarded to the exit interface. In other words, we can say that with fast switching, packet flow information is stored in the fast switching cache memory, and this helps with quick lookup. Cisco Express Forwarding, or CEF in short, is the default behavior on recent iOS versions 12 or later. It provides optimized lookup. It is important to know that with previous forwarding methods, we needed recursive lookup, what we know as recursive lookup, meaning that when we find the best path in the routing table, that gives us the IP for the next hop. Then we need to translate that to the layer 2 address to form the frame and then send it out the exit interface. So we need layer 3 information IP address, we need layer 2 information MAC address. For IP address, to get MAC address, we need recursive lookup from routing table into MAC address table. This is known as recursive lookup. With CEF, unlike the previous forwarding methods, we don't have recursive lookup in order to determine the next hop IP address and the associated lookup. This is because we have two different tables with CEF that performs the same job for us. We have forwarding information base, FIB or FIB, and we have adjacency table. With CEF, we use FIB, which is a copy of the routing table at the end of the day, and we use adjacency table that includes all layer 2 addresses that we need. So, in simple words, we can say with CEF, we already have layer 3 information and layer 2 information needed to form the frame and forward it out the exit interface when we do routing. Thanks to these two tables, there is no need to recursive lookup with CEF. unlike previous forwarding methods. The use of these two tables makes Ceph the fastest packet forwarding mechanism in place. It contains the pre-computed reverse lookup, meaning that we don't need to do the recursive lookup for every packet anymore because we have next hop information, interface and layer 2 or data link layer information in hand, and therefore we don't need recursive lookup anymore. So to recap, Ceph is the fastest, most recent, and the preferred packet forwarding mechanism. It builds a forwarding information base or a FIP as well as an adjacency table. Table entries are not packet triggered with Ceph, like what we used to have with fast switching, for instance. But instead, with Ceph, table entries are change triggered when something changes in the network topology. If there is no change in the network topology, then table entries remain the same for FEB adjacency table. When a network has converged, meaning that we know exactly all the subnets where they are residing at the moment, the FEB and adjacent tables contain all the information a router would require in order to forward a packet. FEB contains pre-computed reverse lookups, next hop information for routes, including interface and layer 2 information. Before I move on to routing in more details, I need to recap how we can get connected to networks. We can have home office scenarios whereby devices might connect as follows. Laptops and tablets, they connect wirelessly to a home router. A network printer, for instance, it gets connected using an Ethernet cable to the switch port on the home router, and then the home router connects to the ISP Internet Service Provider cable modem using the Ethernet cable. The cable modem connects to the ISP network. This is the scenario for home office devices. Then we have branch sites, and in branch, devices might connect as follows: desktop PCs, voice over IP phones, and corporate resources like file servers and printers. They connect to layer 2 switches, firstly, using Ethernet cables. Laptops and smartphones, they can connect wirelessly to WAPs or WAPs or wireless access points. The wireless access points, WAPs, they connect to layer 2 switches using cable connections, using Ethernet cables. And then layer 2 switches, they connect to an Ethernet interface on the edge router using Ethernet cables. You see the role of Ethernet cable between different networking devices or intermediary devices. So again, here layer 2 switches, they use Ethernet cable and they get connected to edge router and the Ethernet interface. Then the edge router in turn connects to a WAN, wide area network service provider, the one that you subscribe to. Then you have central site, whereby devices like layer 2 switches here, they connect redundantly to multi-layer layer 3 switches. So layer 2 switches connect redundantly to multi-layer layer 3 switches using Ethernet fiber optic this time cables because of the speed requirements that we want, or let's say because of the increased speed capacity or speed requirements that we have. Layer 3 multi-layer switches connect to an Ethernet interface on the edge router of the central site, again using Ethernet cables. The corporate website server, probably it is behind the firewall and it connects to the edge router interface. Edge router connects to a WAN or wide area network service provider and also to a secondary ISP or an ISP for backup purpose in case the primary method of connectivity fails. Now that you see how to connect to a network, let's see the role of default gateway. When we are sending a packet to a device, there are two possible scenarios. We can have the destination device residing on the same IP network as the sending device, or in the second scenario, we can have the destination device residing on a different IP network than the source or the sender. No matter which scenario, three pieces of information are required for sending a packet to a device. We need destination IP address, we need subnet mask to know where or which subnet or which network this device or this destination IP address belongs to, and then the default gateway information, DG. With the first scenario, whereby the destination is on the same IP network, router is not involved at all, and packet gets forwarded out the host interface to destination. But in the second scenario, whereby the destination is on a different IP network, then the packet is forwarded to default gateway, and from that place it can get routed to the final destination. So you can see the role of default gateway. When a host sends a packet to a device on a different IP network, the packet is forwarded to default gateway first because the host device cannot communicate directly with devices outside of the local network. Remember, default gateway acts like a taxi, and when you want to get to a remote network, you need a taxi to get there, and the default gateway is that taxi. Is the device that routes traffic from the local network to devices on remote networks, such as devices on the internet, very famous example for it. We know that network administrators, they need to get connected to the networking devices remotely using telnet, using SSH, HTTP, or the secure version of it, HTTPS. For this purpose, network devices, they require IP addresses so that we can manage them remotely for administrative purposes. A switch, in this case, requires an IP address in order to be remotely managed, and this IP address is allocated to what we know as a virtual interface. So switches, they have SVI or switched virtual interface. The configuration that you can see on the top of this slide, in fact, enables IP addresses on switches for this purpose. If you pay attention to the figure on the top, you see switch 1 configuration. You enter interface VLAN 1 in order to assign IP address to switch virtual interface. Then you use IP address, in this case 192.168.10.2/24, and this switch is assigned to VLAN 1 for SVI, for remote management of this networking device. Don't forget you need to also issue no shutdown command just in case if it is shut down by default, depending on the iOS. Next step, we issue IP default gateway command on S1 in order to specify the default gateway on that subnet. So S1 is referring to router 1's gigabit 0/0 interface as the default gateway. Next up, we want to see how routing decisions are made. I want you to understand what we know as a router switching function. Router switching function, don't get it confused with the function of layer 2 switching. It's a different story here. We're talking about routers, so we are in layer 3 and we want to see what router switching function means. We know that the primary function of a router is to forward packets towards the destination. How routers do this? They use what we know as a switching function, which is a process that accepts a packet on one interface of the router and forwards that packet out of another router's interface. As I said, this is not to be confused with the function of a layer 2 switch. With routers, we're talking about layer 3, and the switching function also encapsulates the packets in the appropriate layer 2 or data link frame type depending on the outgoing interface, be it fast Ethernet or PPP, point-to-point protocol, operating over serial links. We can have different layer 2 framing, and it's the job for the router to determine the outgoing interface and according to that to encapsulate the packets in the appropriate data link frame type for the outgoing interface. This is important to know that routers are able to encapsulate as well as de-encapsulate packets. The router switching function can be summarized in 3 different steps. When a router receives a packet from one network and that packet is destined for another network, the router performs these 3 steps. With step 1, router de-encapsulates the layer 2 frame header as well as trailer. Why? In order to expose the layer 3 packet inside the layer 2 header and trailer. So de-encapsulating layer 2 into layer 3 is the first step for router switching function. Then what router does is to examine the destination IP address of the included packet within the frame. So examining the destination IP address of the IP packet in order to find out the best path to forward the packet out, and this best path here is determined by the map that we are having in our hand called routing table. Step 3, if a router finds a path to destination, it encapsulates the layer 3 packet into a new layer 2 frame depending on the exit interface. So encapsulating the layer 3 packet into a new layer 2 frame and then forwarding the frame out the exit interface. This is the third step that a router takes. Very important to remember that as a packet travels from the source device to the very last destination device, what happens at the end of the day is that the layer 3 IP addresses, they do not change. However, the layer 2 data link addresses, they change at every hop depending on the layer 2 protocol operating over the exit interface. So layer 2 data link addresses, they change at every hop as it is de-encapsulated and re-encapsulated again. Now we have an example here when PC1 wants to send the packet to PC2. PC2 is residing 3 hops away, so we want to see what happens at each hop. As the packet travels from router 1 along router 2, router 3, and then the destination. At very beginning of this scenario for PC1 to send the packet to PC2, this is important to remember that we need to forward the packet to the destination that resides a few hops away. So we do not forward to next hop, and we want to see how this is happening. PC1 at the very beginning of this scenario must determine if the destination IP address is on the same network. If it is on the same network, it simply means that PC1 needs to obtain the destination MAC address from its ARP cache memory or use an ARP request, address resolution protocol ARP request. However, in this scenario, the destination network is on a different network. So it's a remote network, and PC1 therefore needs to forward the packet to the default gateway first. Remember, default gateway acts like a taxi to get to the remote networks and remote sites. To determine the MAC address of the default gateway, PC1 needs to check its ARP table for the IP address of the default gateway and its corresponding MAC address. Because before being able to forward any packet further, we need both. We need layer 2 address and layer 3 address. So we need MAC address and IP address. And for a known IP address, to find out the corresponding MAC address, we need address resolution protocol in place. An ARP request is sent if it is not found. When PC1, however, has the MAC address of router R1 in hand, it can forward the packet. Packet gets forwarded to the next hop. When R1 receives the Ethernet frame from PC1, what happens is that R1 first examines the destination MAC address, which matches the MAC address of the receiving interface of R1, and therefore R1 copies the frame into its buffer because he knows that it was destined for him, and therefore it copies the frame into his buffer. R1 then identifies the Ethernet type field. And the value for Ethernet type field, if it is hexadecimal 800, that simply means that the Ethernet frame contains an IP version 4 packet inside the data portion of the frame. Now that R1 has an Ethernet frame in hand, he needs to do the router switching function by firstly de-encapsulating the Ethernet frame to expose a layer 3 IP packet, and then examining the destination IPv4 address of the packet, and in this case we see 192.168.4.10 to be the destination IPv4. As it does not match any of the directly connected networks of which R1 is aware, that means R1 searches the routing table for corresponding route. And imagine at this point of time, R1 has already a route inside its routing table for 191.168.4.0/24 network. So R1 has received the Ethernet frame from PC1, and the route that R1 finds to the 192.168.4.0/24 network has a next hop address of 192.168.22, and therefore the exit interface is fast Ethernet 0/1 on R1. This will require that the IPv4 packet be encapsulated in a new Ethernet frame. As I said, at each hop, we need to create a new layer 2 frame, and the layer 2 protocol depends on the layer 2 technology running over the exit interface or outgoing link. Here, the new Ethernet frame is established with the destination MAC address of the IPv4 address of the next hub router, that is 192.168.2.2. Because the exit interface is on the Ethernet network, that is a broadcast medium type, what happens is that R1 must resolve the next hop IPv4 address with the destination MAC address as before, using address resolution protocol or ARP, assuming it is not inside its ARP cache memory. What happens is that when R1 has the MAC address for the next hop, the Ethernet frame has all information needed to be created and formed, and therefore the Ethernet frame gets established and forwarded out of the fast Ethernet 0/1 interface on R1 router. Same happens on R2 when R2 receives a frame and its fast Ethernet 0/0 interface. We know that this frame needs to be forwarded further to R3. So to get to this point, R2 examines the destination MAC address first, at very first, to see if it matches the MAC address of its receiving interface, that is fast Ethernet 0/0. R2 later copies the frame into its buffer if this match is valid. R2 then determines that the frame contains an IPv4 packet inside the data portion of the frame. How? Thanks to the Ethernet type field, that is hexadecimal 800 in this case, indicating that the Ethernet frame contains an IPv4 packet inside the data portion of the Ethernet frame. To get to the IP inside the data portion of the Ethernet frame, we need to de-encapsulate the frame. And that is what happens now. R2 de-encapsulates the Ethernet frame in order to expose the IPv4 packet inside the data portion of it. So it removes the header and the trailer from the beginning and the end of the Ethernet frame to get access to the actual IP packet inside the frame. Because the destination IP address is on a different network, i.e. 192.168.4.0/24, the routing table is searched in order to find a corresponding route for the destination IPv4 address, that is 192.168.4.10. The interesting point here is that unlike before, the exit interface is not Ethernet anymore. As you can see, it's a serial cable, so it's a point-to-point protocol operating between R2 and R3. That was not the case between PC1 and R1, or between R1 and R2, or between R3 and PC2. They were fast Ethernet connections, and Ethernet was running over these connections. Here we have PPP operating over serial connection between R2 and R3. And that has an implication here. Imagine that R2 inside its routing table has a route to 192.168.4.0/24 network with the next hop IP address of 192.168.3.2 and exit interface to get to the final destination is serial 0/0/0. But because the exit interface is not Ethernet anymore, R2 does not have to resolve the next hop IPv4 address with the destination MAC address. So this is different from what we had with Ethernet type of connection here with PPP and serial connections. This is very important to know that we do not have MAC addresses on serial links. So if next hop is not Ethernet, then that means we don't need to resolve next hop IP to MAC address because there is no MAC address on serial. So for this reason, we need to set the destination MAC address to broadcast. So once again to recap, because the exit interface is not Ethernet, R2 does not have to resolve next hop IP address with the destination MAC address because there is no MAC address defined on serial cables. What happens as before is that IPv4 packet at each hop needs to be encapsulated into a new data link frame determined by the layer 2 protocol running over the exit interface. So new data link frame will be formed and will be used by the exit interface, and in this case it will be sent out the serial 0/0/0 exit interface. Because there are no MAC addresses on serial interfaces, and I keep repeating this because it is very important, R2 sets the data link destination address to an equivalent of a broadcast, that is FFF address. So simply the point that there are no MAC addresses on serial interfaces, that doesn't mean that we do not need to put anything inside the MAC field of the frame. As I said before, in order to send a packet from very initial source PC1 in this case to very final destination PC2, at each hop we need two important pieces of information, and that is IP and MAC. And here, since we don't have any actual MAC address because of the serial interface and serial connection usage, we need to put value inside that, and that value is an equivalent of a broadcast address, and that finalizes the data link layer frame establishment. So R2 sets the data link destination address to broadcast. We then get to the R3. In order to get to the destination, R3 copies the data link, in this case PPP frame, because we are using point-to-point protocol over serial connection here, into its buffer. Remember, there is no need to match MAC address here to see if it was correctly destined to this, because there is no Ethernet connection anymore. There is a PPP over serial link, so we directly copy frame into the buffer. And R3 now needs to de-encapsulate the data link PPP frame in order to expose the IP address and IP packet itself. What happens is that R3 searches the routing table as before for the destination IPv4 address of the packet, that is 192.168.4.0/24 for the network, and the 10 for the destination IP address here, PC2. Because the destination network is on R3's directly connected networks listed under the routing table, the packet can be sent directly and does not need to be sent to another router anymore. Since the exit interface is a directly connected Ethernet network, R3 must resolve the destination IP address of the packet with the destination MAC address by either finding it inside the ARP cache memory or sending out an ARP request. And this is exactly as what we had before at each hop. In order to gain MAC address information when we have the IP address, we use ARP request, or if we already request that, we can use ARP cache memory. So this finalizes the process for PC1 to send the packet to PC2 in this scenario. The takeaway points, again, remember, next hop, if it is not Ethernet, there is no need to do resolving for IP to MAC because there is no MAC on serial lanes. We need to set the destination MAC address to broadcast address. And R3, as we have seen, unlike R2 and R1, the encapsulates layer to point frame instead of the encapsulating Ethernet frame. The primary function of a router, to recap, is to determine the best path to send packets. We have seen how we are using routing table searches in order to find the path or the route to destination. 3 path determinations we may have directly connected firstly, or if the destination is residing inside remote network, or thirdly, if no route determined at all. Directly connected network, as we had this with R3, if the destination IP address belongs to a network that is directly connected to the router, the packet is forwarded out of that interface and that's it. If the destination is within a remote network, as we had with R1 or R2 in this scenario, if the destination IP of the packet belongs to a remote network, the packet is forwarded to the next hop router or another router. And then with no route, if there is no route found inside the routing table, no directly connected or no remote network, then what we're going to have is that the destination IP does not belong to a connected network or is not listed inside routing table entries, and therefore the packet is sent to what we know as gateway of last resort. And we will explain that later when we explain static routes, and you will see example of that. Static routing is our next stop. A router learns about remote networks in 2 different ways, either manually or dynamically. Manually entered into the routing table using what we know as static routes. And that is going to be the topic of discussion here. Static routes are not therefore automatically updated, unlike dynamic or automatic routing. So second type, dynamically or automatically learned routes using routing tables. With static routing or with static routes, remember, it must be reconfigured if the network topology changes in any way. So when topology changes happens, what happens is that you as the network administrator have to reconfigure the network and revalidate the static routes configurations. With dynamic or automatic routing, we don't have this problem because they have learned how to adapt to changes of the network. We're going to discuss different use cases for static routes. Very first scenario here is the use of static routes for smaller networks. If you have smaller networks that you expect that these networks do not grow over the time, then probably a more reasonable choice is to use static routing instead of dynamic routing. The second use case or second scenario for static routing is routing to and routing from stop networks. Stop network, or let's say stop router, is a router with only one upstream neighbor router. Routing to and routing from these stop routers is handled with static routing. Stop network is accessed by a single router, only one neighbor, and this makes stop network suit static routing. Third scenario, the third use case that we're having is a very important one. This is known as default route. So a single default route to represent a path to any network not found in the routing table. So in case we don't find any match in the routing table entries for the destination IP address of a packet, and in case that the default route is already configured, a single default route represents a path to any network, and therefore that specific network in this case not found in the routing table. Let's see static routes types in more details for these scenarios. When we use static routes, firstly, when we want to get to specific network. So to connect to a specific network, we may use static routes. We may use static routes secondly, as I said, to connect a stop router. And a stop router is defined as a router with only one upstream neighbor router. This is the second static route type. And the third static route type is summarization, or summarizing routing table entries in order to reduce the size of routing advertisements. And we need this for our efficiency in the network, because with reduced size of routing advertisements, we're going to have more efficient routing. Fourthly, we may need to use static routes in order to create a backup route. And we need a backup route in case the primary route link fails. Static routes enable us to define a backup path in case the primary failed. Now that you have seen different scenarios and use cases for static routing, I would like you to know more about them in details with A, B, and C. The A is default static route, B is summary static, and C is floating static route. Let's start with default static route. Default route, as I said before, matches all packets and is used in case a packet does not match a specific route in the routing table. So you don't have any specific route in the routing table matching the destination IP address of a packet. And if the default static route is already configured, you don't need to discard the packet, because you know where to send it in case no any other match found in the routing table, or any specific match found in the routing table. This default static route can be learned dynamically or statically, but our focus here is static routing, so we want to see how to configure it statically. Default static route uses what we know as quad zero network. Quad zero network is equivalent to 0.0.0.0 with subnet mask 0.0.0.0 in IPv4. If you put this one as destination IPv4 address, that simply means that none of the bits are required in the destination IP address for the incoming packet to match, and in other words, it means that everything matches and this default static route can be used. If you issue show IP route static, you see all static routes defined on that route, including default static route. And on the routing table, you can see S to stand for static route, indicating static route. You see star sign or asterisk, which indicates the candidate default route for default static route, and then /0. This mask in the route entry indicates none of the bits are required to match, and in this way we can verify the existence of default static route. One important point here is that when you create a default static route, what happens is that it creates a gateway of last resort, and the gateway of last resort can be verified on the routing table as well. And that means that if there is no other routes in the routing table matching the destination IP address of the incoming packet, this default route can be used as the gateway of the last resort. I would like you to know about two common use cases for default static routes. So default static routes are commonly used when connecting, firstly, an edge router to a service provider network, and secondly, when a stub router or a router with only one upstream neighbor router is concerned. Two similarities between both scenarios or use cases for default static routes here. One is the fact that each router has only one router to which it is connected. And the second similarity is that with both cases, we don't have any automatic or dynamic routing protocol in place. And in fact, we don't need them. And when there is no other route in the routing table matching destination IP address, the default static route will be used to get to either a service provider network or to an upstream neighbor router in case of stop routing. Next is summary static route. Multiple static routes can be summarized into a single network address. For this, destination networks must be contiguous. This is very important. Also remember, multiple static routes must use the same exit interface after summarization or the same next hop. Third category here, very important one, floating static routes. These are static routes that are used in order to provide a backup path, used when primary route is not available anymore and it fails, backup takes over. For this purpose, we need to configure floating static routes with a higher administrative distance. You know that administrative distance indicates the trustworthiness of the route. So the higher the AD, the less preferable that route is. For this purpose, we need to configure higher AD than the primary route. In case primary route fails, backup takes over. For instance, with EIGRP AD is 90. A floating static route with an AD of 91 or any number higher than 90 would serve as backup route in case EIGRP path fails and will be used if EIGRP route goes down immediately. Very important to remember that by default, the AD of static route is 1. Static route AD can be increased to make route less desirable until preferred route is lost. Let's see one example from IPv4, one example from IPv6 for floating static routes. For IPv4, if you issue IP route quad 00000 and the subnet mask 0000, and then specify the next hop address, let's say 172.16.2.2. This is the primary route. For static route, we have configured with static route, and now if we issue IP route, same network quad 0, 0.0.0.0 with subnet mask 0.0.0.0, and then we put another next hop to form the backup path, let's say 10.10.10.2 with higher AD. In this case, we put 5 at the end of this command, and this 5 is the administrative distance we have entered manually. Now, if the next hop 172.16.2.2 fails, then the backup path with next hop address 10.10.10.2 will take over. So the preferred router is the one with AD equal 1. The default for static route that is 172.16.2.2 in this example, but in case it fails, 10.10.10.2 with AD5 is the next preferable route. We have identical configuration for IPv6. So you issue IPv route ::/0, indicating the equivalent quad 0 network in IPv4. Here we have : :/0. Next hop, let's say 2001 :db8 :acad :4 :2. This is the primary route, and the backup path is IPv6 route : :/0 2001 :db8 :acad :6 :2, and we enter the AD for the backup path. In this example, again, we use number 5. So the preferred router is still the one with IP address, IPv6 address 2001, so 2001 :db8 :acad :4 :2 with AD1, and the backup path in case the primary route to this host fails is the one with the next hop 2001 :db8 :acad :6 :2 with AD5. Remember, we have the common iOS troubleshooting commands. You need to remember them: ping, trace route, show IP route, show IP interface brief, and show CDP neighbors detail. These 5 form the basic troubleshooting commands and the ones that we're using commonly. In these 2 examples, IPv4 and IPv6, we have first set the primary path by indicating the next hop with AD1, and then the backup path with next hop using the higher AD, in this case number 5. Now we want to see what happens before actually packet is forwarded to the router or the hop that is our neighbor. This is known as route resolvability. Before packet is forwarded, our router must determine the exit interface. So the way that it works is that we use one of these 3 approaches. We firstly may only show the next hop IP address, as it was the case with IPv4 and IPv6 examples that I just mentioned. Second approach is to use the exit interface on the local router. So first next hop IP address, second exit interface on local router. And the third approach is the combination of first and second approaches. So this is called fully specified. This is where we use not only next hop IP addresses, but also exit interface on the local router. So in a static route, next hop can be identified by next hop IP address, router exit interface, and thirdly by combination of next hop IP address and exit interface. this happens before packet is forwarded to the next hop, and this is required in order for the router to determine the exit interface first. The exit interface to be used by that router before forwarding the packet. This must be clear, and this is known as route resolvability. This is very important to remember that when you are indicating the place that the packet must be forwarded to through the next hop IP, then this approach creates what we know as a recursive lookup, meaning that all the information that we have in hand is the next hop IP address. But for the router to be able to forward the packet, he also needs to know about the exit interface. For this, he needs to translate the next hop IP address into the corresponding exit interface. And this approach, behind the scene, imposes another lookup known as a recursive lookup to find out what the associated exit interface with the next hop IP address is. So router searches again inside the routing table, this time not for the sake of finding a match for destination IP address inside the packet, but instead in an attempt to find out what next hop IP address network is, and inside the routing table he wants to find out what the associated exit interface looks like. However, if you are using the second approach, i.e. exit interface of the router, and you define a static route using an exit interface instead of the next hop IP address, what happens is that there is no requirement for lookup anymore, so no other lookup needed, and router knows exactly how to forward the packet. So we can say in theory this is more efficient. Next, a bit of more discussion on IPv6. You already saw how we are using IPv6 commands in order to define default static route for IPv6. The same command here, it is IPv6 route, IPv6 prefix, and slash and prefix length, and either IPv6 address or exit interface, or combination of both in case you're using the fully specified approach. With IPv6 prefix, destination network address of remote network to be added to routing table is intended. Prefix length of remote network to be added. And then we have IPv6 address. This is exactly next hop IP, commonly referred to as next hop IP. And a very important point here, next hop IP typically is used when connecting to a broadcast media, i.e. Ethernet. And as I said, it commonly creates a recursive lookup. However, you can use the second approach with exit interface that is more efficient because you don't need to do recursive lookup anymore. You use outgoing interface to forward packets to destination network. This approach is also referred to as a directly attached static route, just the name for it. And exit interface is typically used when connecting in a point-to-point configuration, unlike next hop IP that is used when connecting to a broadcast media like Ethernet. Similar to IPv4, we must resolve the route to determine the exit interface before being able to forward the packet. Again, next hop can be identified by an IPv6 address, as I said, exit interface, or both for fully specified approach. So we can have next hop static IPv6 route, and this is when only the next hop IPv6 address is specified. There is a bit of a warning here. Remember, when using next hop IPv6 address, you cannot use link local IPv6 address unless you are using fully specified approach. So fully specified static routes must be used if IPv6 link local addresses are used as next hop IPv6 address. Second approach, directly connected static IPv6 route, only the route exit interface is specified. And the advantage of second approach is that you don't need any other lookup, and therefore it is more efficient. And the third approach, fully specified static IPv6 route, when both the next hop IPv6 address and exit interface are specified. In this case, you can use IPv6 linked local addresses because you are also adding the exit interface. What you see here with default static IPv6 route is exactly what I mentioned earlier with IPv4 and also IPv6 example that we had with floating static routes. Both IPv4 and IPv6 default static route is supposed to match all packets not specified inside routing table. So ::/0 mask indicates that none of the bits are in fact needed to match. And if a more specific match does not exist, then that means that default static IPv6 or IPv4 route matches all packets. One point at this place to remember always and always that you need to use IPv6 unicast routing first, and then you can start configuring IPv6. So IPv6 unicast routing is needed in order to enable router to forward IPv6 packets. This is not on by default at the moment. You need to enable it first, and then you can define IPv6 commands like this one for default static route or any other IPv6 configuration. So IPv6 unicast routing first, always. Last but not least, as soon as you define an interface, you assign IP address to it with a 32-bit mask or with 128-bit mask in IPv6. What happens is that if you go on the routing table, show IP route, you see what we know as host route. Host route is a very important concept. It is automatically installed when an IP address is configured. As soon as an IP address is configured, it is added to the routing table, and it is indicated with L. L stands for local route, so local route marked with L, and this is known as host route because it is configured as a static host route. It allows more efficiency for packets directed to that router. So you see L and you see also C connected for directly connected networks, and then L for host route, or what we know as static host route. Next up is dynamic routing. We want to see very firstly the purpose of dynamic routing. Also, we want to get familiar with concepts like metrics, convergence, stance vector, link state, classless, classful, interior gateway protocols or IGP, and exterior gateway protocols or EGP. What are the purposes for dynamic routing protocols? Firstly, discovery of remote networks. is what we are looking for with dynamic routing, maintaining up to date routing information. Thirdly, to choose the best path to destination networks. And fourthly, the ability to find a new best path if the current path is no longer available. If the primary route fails, we want the backup route to take over. These four form the main purpose for having dynamic routing protocols. For these four dynamic routing protocols have certain components. The main components of dynamic routing protocols include data structures, routing protocol messages, and protocol algorithms or routing algorithms. Data structures, what we mean is in fact tables and databases that are kept inside RAM memory, random access memory. We have routing protocol messages in order to discover our neighbors. So they help us discover neighboring routers, and then they help us exchange routing information and maintain accurate information about the network. Thirdly, we have algorithms in place, and they are here to facilitate learning routing information and also help us choose the best path. So, for best path determination, we need certain algorithms, and each of these routing protocols, like EIGRP or OSPF, they're depending on different routing algorithms. We have previously seen how networks can be learned. Remote locations or remote networks, they can be learned statically or dynamically. And that's why we have static routing, dynamic routing in place. We use static routing when we have small networks. For easy routing table maintenance in small networks, we use static routing. Also, for routing to and routing from a stop network, the best solution is static routing. Finally, to access a single default route, we use static routing. On the other hand, we have dynamic routing, and dynamic routing is the best choice for large networks as opposed to static routing and small networks. Dynamic routing protocols, they help the network administrator manage the network and also help provide redundant paths, so we can inject redundancy into our network, so when the primary route fails, we can still route our traffic through the secondary routes to destination. Dynamic routing help automatically implement the alternate path. When a primary link goes down, the alternate path takes over. The table towards the top of this slide is weighing up the advantages and disadvantages of static versus dynamic routing paradigms. Let's first investigate the advantages of static routing. Static routing is easy to implement. This is very important. Static routing is secure. Why? Because there is no update mechanism in place to send advertisements, and that means that we're going to have secure routing because we are not relying on other entities or other messages that can be impersonated by attackers. Another advantage of static routing is that we know exactly where we are heading to. In other words, we always have same route to destination. Finally, we have no algorithm or update mechanism required with static routing, and that really means that We are not having our resources engaged, so no CPU, no RAM are involved in static routing as opposed to dynamic routing for the sake of route calculation. Having said that, remember that static routing very well suits simple topologies. And when networks are too large, then they get complex if you use static routing for large networks and topologies. So static routing only for simple topologies or for special purpose like default static route. And we have default static route when we want to direct traffic from our LAN towards the internet, for instance. So remember complexity of static routing as network grows, and also static routing asks for manual intervention to reroute traffic because static routing does not automatically adapt to network topology changes. When we have large networks with multiple routers, then dynamic routing is the best option. So dynamic routing is suitable when multiple routers are involved. And the good news with dynamic routing is that it is independent of network size and it very well fits with large network topologies. With dynamic routing, it automatically adapts topology to reroute traffic if possible. For instance, we can have load balancing in dynamic routing. We can have, let's say, half of traffic going through route A and another half going through route B, but both towards the same destination. These advantages of dynamic routing, however, come at a cost. Dynamic routing is more complex to implement, firstly. Dynamic routing is less secure than static routing, and dynamic routing requires additional settings to cater for security. Route and let's say routes in dynamic routing, they depend on current topology. If there is a change in topology, dynamic routing needs to adapt to changes. And for this purpose, it requires additional resources, and resources include CPU, RAM, and bandwidth. So all these routing updates that are supposed to be transmitted as soon as there is a change in the network, they consume link bandwidth. They require router CPU and RAM to get involved for route calculation or for recalculation. And that's why we can say here that it requires additional resources. We have two classes of dynamic routing protocols. We have interior gateway protocols, first class, and the second class we have exterior gateway protocols. So IGPs and EGPs. EGPs, they operate between ISPs, so between internet service providers. For exterior gateway protocols, we have another term here. We call it path vector routing protocol, and for the de facto one in today's internet, the protocol is called BGP, Border Gateway Protocol. For IPv4, we have BGP version 4 in place, and for IPv6, we have BGP multi-protocol or BGP MP in place. They are categorized under path vector routing protocols under exterior gateway protocols. Interior gateway protocols have two subclasses. We have distance vector interior gateway protocols on one hand, and on the other, we have link state interior gateway protocols. Distance vector interior gateway protocols for IP version 4 include RIP version 2 or Routing Information Protocol version 2 and EIGRP Enhanced Interior Gateway Routing Protocol. These two distance vector interior gateway protocols operate for IP version 4. Distance vector interior gateway protocols for IP version 6 include RIP-NG or RIP Next Generation, and we have EIGRP for IPv6, another distance vector interior gateway protocols alongside RIP-NG. The second subclass of interior gateway protocols is link state. So link state routing protocols, we have OSPF version 2, and OSPF stands for Open Shortest Path First, OSPF, and version 2 of this protocol is for IPv4. Version 3 of this protocol, OSPF version 3, operates for IP version 6. We have also ISIS, intermediate system to intermediate system, another link state interior gateway protocol alongside with OSPF, and ISIS operates for IPv4, and we have another variant of it called ISIS for IPv6. As the name suggests, it works for IP version 6. So OSPF and ISIS, they are link state interior gateway protocols. RIP and EIGRP, they are distance vector interior gateway protocols. We have path vector exterior gateway protocol. Here we only go through BGP border gateway protocol that operates between ISPs. The very first interior gateway protocol to touch here is distance vector 1 RIP routing information protocol. RIP protocol was updated to RIP version 2 to accommodate growth in the network environment. RIP version 2 does not scale to current larger network implementations, however. Remember that we have hop limit for it, and hop limit is 15, so 16 hops away is unacceptable. That's why we have other routing protocols in place, and they have been developed to meet the need of larger networks that we have in today's world, including OSPF, ISIS, EIGRP, and BGP between ISPs. But let's start with RIP. You see the configuration here. You need to issue router RIP on Cisco routers to enable RIP version 1. And if you negate this command, if you put no in front of it, no router RIP, then you disable routing information protocol RIP protocol. What you can see is that after you enable RIP on a Cisco router, then you need to issue network command, and the structure for this command is that you put network and then network address in front of it. This is a router configuration mode command that enables RIP on all interfaces that belong to a specific network. This is very important. Any interfaces under the network address highlighted in blue in my slide here starts advertising the network address in RIP updates every 30 seconds. So advertises the network in RIP routing updates sent to other routers every 30 seconds. We have RIP version 1 and RIP version 2. The difference is that RIP version 1 is a classical routing protocol for IPv4. To accommodate for the growth of networks and to support subnetting, we need to activate RIP version 2 so that it can support subnetting concept and VLSM to be able to carry the subnet mask inside the routing update and routing advertisements. If at this point of time you issue show IP protocols command, it displays IPv4 routing protocols, all routing protocols configured on that router. And so far you see only RIP version 1. Also, if you issue show IP root, it displays all RIP version 1 routes installed in the routing table on that router. However, if you use the version 2 command, that is a router configuration mode command, then you enable RIP version 2 instead of RIP version 1. RIP version 2 automatically summarizes networks at major network boundaries, however. So you need an additional configuration here. No auto summary command. Again, no auto summary. Router configuration mode command. It disables auto summarization. And now, if you issue show IP protocols again, then you can verify that auto summarization by RIP is off, is disabled. One very important point about RIP updates is the fact that RIP updates are forwarded out all RIP enabled interfaces by default. And as I previously mentioned, when you issue network command, it enables RIP on all interfaces that belong to that given network address. But the point is, we only need to send RIP updates out interfaces that are connected to other RIP enabled routers and not to every interface that comes under the network address, because we may have some PCs attached to that interfaces or other LANs that they don't need to hear about it, instead of RIP enabled routers that need to operate with other RIP routers. Sending RIP updates to LANs, for instance, it wastes bandwidth, wastes resources, and is a security risk, of course. And that's why we use the passive interface router configuration command in order to stop routing updates being advertised out the irrelevant interfaces like LAN interfaces. So non-RIP router neighbors, they don't need to receive updates. That's why we need to use passive interface command. It still allows that network, let's say that LAN network, to be advertised to other routers. But that LAN itself, it won't receive routing updates for RIP in this case. So once again, router RIP command enables RIP on all interfaces that belong to the given network, and this is not limited to neighboring RIP routers, while it should be. And for this reason, we need to use passive interface router configuration command to stop routing updates out those interfaces, because we don't want LANs, for instance, to receive RIP routing updates, because sending RIP updates to LANs wastes bandwidth, wastes resources, and is a security risk. Next, how to propagate default route. Refer to the diagram towards the middle or bottom low of this slide. What you see is a topology. In this diagram, a default static route to the internet is configured on R1. Default static route provides a path towards the internet cloud, and now we want R1 to advertise this default static route to other routers, R2, R3, etc. The default information originate router configuration command is what we need. It instructs R1 to send the default static route information in the RIP routing updates. So the commands that we need to provide an R1, we use IP root quad zero network, so 0000, then subnet mask 0000. Then we specify the outgoing interface serial 0/0/1, and the next hop for internet cloud, in this case 209.165.200.226. This provides the default static route. We want to propagate it to other routers in the REAP domain. So we issue router REAP, and then under router REAP, we issue default information originate to propagate the default route. Next step is to analyze routing table entries. We already have seen host root is an IPv4 address with a 32-bit mask, or in case of IPv6, we have IPv6 address with a 128-bit mask. So it is automatically installed when you configure an IP address, and it is configured as a static host root, they call it host root, and it is marked with L, so local root marked with L in the most recent iOS versions, and then it allows more efficiency for packet directed to that router. But L is not the only entry that you add to the router automatically when you configure an interface. You also define directly connected networks, or C. So directly connected networks are automatically added to the routing table as well when the interface is configured and activated. So no shutdown command is issued. If you do show IP route to display the routing table as soon as you configure an interface, no matter IPv4, IPv6, and then you issue no shutdown to activate it, then what you see is the routing table entries. And entries in the routing table, they contain some important information we should be aware of. At the very beginning, we can see root source towards the left, the first column. As you can see in this slide, root source is there to tell you how the root was learned initially. So you can see C and L, C for directly connected networks and L for host root or static host root as soon as you configure an interface and activate it. So a 32-bit mask for that interface, or in case of IPv6, 128-bit mask. Next, what you can see is the destination network. And destination network in the routing table means the remote networks that we have been learning either statically or dynamically. Next to remote network or destination network, what you see is outgoing interface. So in case of host root or directly connected networks L and C, you can see outgoing interfaces being listed next to the networks. So exit interfaces used to forward packets to destinations are detailed, and then if you have other routing protocols configured on that router, then you can see the root source for them. In this case, we have R. R stands for RIP routing protocol. You may have O for OSPF routing protocol. You may have D for EIGRP routing protocol. D stands for Dijkstra's algorithm inside EIGRP. This is the algorithm that EIGRP relies on. Or you can see S for static root. As I said, we already defined IP root quad zero network, the default static route towards the internet cloud for instance, and we have also propagated the default route to other routers. The routing table in this diagram is for R1. These were information that basically L and C routes are having inside the routing table. But as you can see with other root sources like R for REAP in this case, more information is displayed and we want to analyze that information as well. So root source for R roots are the same. This is how the root was learned. Destination network the same. But very important one, what you can see here for this root, for instance, R192.168.3.0/24, then what you see is 120/1. What is this bit of information here telling us? So administrative distance, in this case 120 AD, is indicating the trustworthiness of the root. In this case, RIP root, so the AD is 120. Then next to that, after the slash, you see 1. This is the metric, and the metric is the value assigned to reach the remote network. The lower the metric, the better. So we always prefer lower metric. Same for AD, we always prefer lower ADs if we have more than one root source. Let's say we have learned about a remote network from two different root sources, one RIP with R, another one with O for OSPF. The one that has lower AD is the preferred one to get to that single specific network that we have learned through two different root sources. Next bit of information for this specific example of RIP root is next hop. This is the same as L and C routes that we have seen initially. You can see IPv4 address of the next router that the packet should be forwarded to. We also have what we know as a route timestamp as the next bit of information here. And this is the time since the route was updated. So you can see here 000008. This is the time since root was last updated. And then outgoing interface is the last entry. Exit interface to use, of course, to forward the packet. Some specific terms for routing table you should be aware of. The routing table is a hierarchical structure. And the reason for having this in hierarchy is that we want to speed up the lookup process when we want to locate routes and forward packets. We have four different terminology, different terms to be used with this hierarchy inside routing table entries you should be aware of. We have level 1 ultimate routes, we have level 1 routes, we have level 1 parent routes, and we have level 2 child routes. So level 1 ultimate routes, level 1 routes, level 1 parent routes, and level 2 child routes. What is level 1 ultimate routes? An ultimate route is a routing table entry that contains either a next hop IPv4 address or an exit interface. Based on this definition, you can say that all directly connected routes, all dynamically learned routes, and local routes are all considered ultimate routes. So let's refer to our example here. The first route that you can see here, 192.168.1.0/24, this is not an ultimate route because the information in front of it does not specify neither next hop IPv4 address nor an exit interface. That simply means that if you go here, 192.168.1.0/24 is not an ultimate route, whereas 192.168.1.0/24, this second entry that is a directly connected network, is an ultimate route because the exit interface has been specified gigabit Ethernet 0/0. So all CNL entries are ultimate routes, as you can see, because they have uh, either next hop or exit interface. Same for dynamically learned routes, like here RIP are routes here. You can see that it has both next hop as well as outgoing interfaces. So these are ultimate routes. Next term to be aware of is level 1 routes. A level 1 route can be a network route, can be a supernet route, or can be a default route. In fact, level 1 routes are distinguished based on the subnet mask that they have. So, a network route that has a subnet mask equal to the classful mask of that network is considered a level 1 route. So, a network route that has a subnet mask equal to that of the classful mask that identifies a level 1 route. Level 1 routes can also be of supernet routes types. So a network address with a mask less than the classful mask is considered supernet route. For example, a summary route or a summary address is considered a supernet route because it has a mask less than the classful mask for that network. For example, 192.168.0.0/16, this route with subnet mask 16 is a summary address, is a supernet route, and therefore is considered as a level 1 route. Thirdly, we have default route as another instance of level 1 route, a static route with the address 0.0.0.0/0 quad 0 network. This is also considered a level 1 route. Now, if you refer to the example that we have here, we don't have any supernet route to show, so we don't have any summary address with the subnet mask less than the classful mask, but we have network routes whereby the mask is equal to that of the classful mask. So here, for instance, we have 192.168.1.0/24. The classful subnet mask for this network, ignoring /24 here, is again /24. So these two are equal, and that's why this is considered as a level 1 route. Same for any of these routes that have been learned by RIP. We again have /24 and /24 subnet mask for these remote networks are equal to that or to those of the classful subnet mask for 192.168 networks, and therefore they are all considered as level 1 routes. We have also quad 0 network here, and the default route, static route with the address 0.0.0/0. This is also considered as a level 1 route, of course. We then have a new concept for this hierarchy known as level 1 parent routes. And a parent route is a level 1 network route that you have previously seen that is subnetted. So any A.B.C.D that it says in the routing table that it is variably subnetted into, let's say, n subnets with m masks, this is considered as a level 1 parent route. Looking at the example that we are having here, level 1 parent routes in the routing table, in fact, provides some sort of heading, let's say, for a specific subnet it contains. So 192.168.2.0/24, as the routing entry suggests, is variably subnetted into two subnets and two masks, n subnets and masks, with other examples, for instance. And based on this information here, you can see that it contains subnets, and in other words, it is a level 1 parent route. It's a parent of subnets. Next is level 2 child routes. Level 1 parent routes, as I said before, contain level 2 child routes. Children, or a level 2 child route, is a route that is a subnet of a classful network address. Level 2 child routes are also ultimate routes, meaning that they either have next hop IPv4 address or exit interface. So we know exactly where to go. Bear in mind that not all ultimate routes are level 2 child routes, but all level 2 child routes are also ultimate routes. Next, we have router lookup process. If the best match is a level 1 ultimate route, whereby we know where to go, next hop IPv4 address or exit interface is determined already, then this ultimate route is used to forward the packet. Lookup process continues if the best match is a level 1 parent route. The router needs to see who the children are, so the router then examines child routes or the subnet routes. If there is a match with a level 2 child route, then that child route is used in order to forward the packet. If there is no match with any level 2 child routes, the router searches level 1 supernet or default routes afterwards. So after examining the children, if there is no match with any level 2 child routes, the router searches level 1 supernet or default routes. If there is a match, well, take that route and that route is used. So supernet or default route is used. Otherwise, if there is no match found in the routing table at all, then the packet is discarded or dropped. This is the router lookup process. Also bear in mind that the best route is always the longest match. So if we have more than one entry in the routing table matching the destination IP address of the packet, the tie-breaking criterion is the longest match. So the best route is always the longest match, meaning that the best match is the route in the routing table that has the most number of far left matching bits with the destination IPv4 address of the packet. This is known as the best route or the longest match. The route with the greatest number of equivalent far left bits, or the longest match, as I said, is always the preferred route. And this is the same with IPv6 entries in the routing table too. Speaking of IPv6 routing table entries, remember that an IPv6 routing table includes directly connected routes, static routes, and dynamically learned routes, very similar to what we have had with IPv4. However, unlike IPv4, with IPv6
all IPv6 routes are level 1 ultimate routes. They don't have hierarchical structure anymore as we used to have with IPv4 routing tables. Here, all IPv6 routes are level 1 ultimate routes. If you issue the command show IPv6 route, then what you see is the content of the IPv6 routing table. So this command is used to display that. And there you can see all directly connected IPv6 route entries as well as all removed IPv6 route entries learned statically or dynamically. With directly connected IPv6 route entries, particular pieces of information can be verified. At very first, you can see root source for directly connected IPv6 route entries. You can see how this route is learned for directly connected. It is indicated with a C and with a L for local route under the routing table. Also, you can verify the network address for the directly connected routes. Then next piece of information is administrative distance or AD, telling you the trustworthiness of the route. The lower the AD, the better. So lower AD means this route is more trustworthy. Next piece of information is the metric, and the metric is the value assigned to reach the network. The lower the metric, the better. Similar to AD, the lower the better. Preferred route. Last piece of information to be observed with directly connected route entries is outgoing interface, by which you can see the exit interface that is used in order to forward packets. In addition to these pieces of information to be verified for directly connected IPv6 route entries, for removed IPv6 route entries, we can see these following pieces of information. You can see root source again. This time, root source is supposed to tell you the route was learned through which routing protocol algorithm. The common codes include O for OSPF, D for Dijkstra for EIGRP routing protocol, R stands for RIP, and S for static route if remote IPv6 route entry is learned statically. Next piece of information to be verified for remote IPv6 route entries is next hop. And with next hop, it identifies the IPv6 address of the next router to forward the packet to. So what we have seen with IPv6 routing table entries is pretty much the same as what we saw with IPv4. For IPv6 router lookup process, similar to IPv4, always remember this rule: the longest match is the best match. So if you have more than one entry matching the destination IPv6 address of the packet inside your routing table, then the longest match is the best one and is the preferred one. And as I said, all IPv6 routes, they're considered as level 1 ultimate routes. That means that IPv6 router examines level 1 network routes for the best match, and if the match is found, it just forwards it to the next hop using the next hop information or the outgoing interface information. More than one entry, then the longest match is winning the competition.